In part 1, we saw that the transmission line is nothing more than a series of inductance and resistance and shunt capacitance and conductance distributed along the wire. Assuming the wires being perfect conductors separated by perfect dielectric, then the series resistance and the shunt conductance can be ignored from the model. We can't consider it as a single inductor and capacitor, because the line is very large compared to the wavelength of the signal. At the same time, the signal has finite traveling speed, so we can't ignore the time delay, and hence the voltage difference between any 2 points on the line. So we divided the transmission line into smaller sections. The length of each is too small compared to the signal wavelength, so that we can ignore the transit time effect at each section. Hence, each section is a series inductor and shunt capacitor. And we saw that this infinite number of inductors and capacitors is equivalent to a real impedance called characteristic impedance. This impedance does not absorb power. It only establishes a relationship between the voltage wave and the current flowing in a line. Before reaching the load, while the signal is traveling through the line, it is still blind to any kind of termination on the line. It can only see the characteristic impedance of the line. By reaching the load, if the load is equal to the characteristic impedance, the signal would dissipate completely in that load. If the load isn't equal to the characteristic impedance, only a portion of the signal is dissipated in the load, and the rest of the signal is reflected back. That reflection is governed by the backward traveling wave in the solution of the voltage and current wave equations. We will talk about reflections in more details, but now, let's assume that the line is infinitely long, so the signal will never reach the load. There is only forward wave. There is no backward or reflected wave. In other words, let's see what happens to the signal while traveling through the line before reaching the load. Suppose we have a transmission line of 50 ohm characteristic impedance. To see what exactly happens inside that line, we will insert its equivalent circuit into the simulator, a 500 sections of series inductors and shunt capacitors. The value of each inductor and capacitor is 20 picohenry and 20 femtofarad respectively. The more sections we have, the more accurate the model. But this is more than enough to get inside of what's happening inside the line. For the case of that discussion, let's apply 1 volt step voltage at the input of the line. The voltage source is having 200 ohms output resistance. From the voltage source point of view, as we saw in the last video, the transmission line has a well-known input impedance, so it behaves exactly as a resistor of a value square root of L over C, the characteristic impedance of the line. It's a voltage division circuit, and the 1 volt step voltage will split as 0.8 volt and 0.2 volt between the two resistors. So the voltage at the input of the line settles at 0.2 volts. At the same time, the current drawn by the line settles at 4 milliamps. Let's examine how the wave behaves at each section in the first trip before reaching the load. From the equivalent circuit, the current entering the transmission line is equal to the voltage from the source divided by the source resistance and the characteristic impedance, and can be modeled as a constant current source having that value. Let's zoom into the first section to see what exactly happens. After that section, the signal sees a resistance equal to the characteristic impedance, so the rest of the circuit can be replaced with that resistance. Now constant current source means that this inductor is a short circuit. In other words, the circuit at the first section behaves exactly as a current source driving a parallel RC circuit. Parallel RC circuit driven by constant current source. The voltage across the capacitor increases exponentially to 0.2 volts with time constant RC, while the current drawn by the capacitor decays exponentially to 0 by the same rate. Since the sum of two currents is constant, the current entering the resistance is increasing exponentially till reaching the value of the constant current source, when the current in the cap reaches 0. Notice that the resistance Z0 contains all the remaining sections. With the help of simulator, we can get the voltage waveform across the first capacitor, and current injected into the adjacent LC segment. Very similar to the approximation we made. These graphs represent the voltage and current at that location on the line. Now let's move on to the next section. We saw that the current entering the resistance, or the current entering the second section, is increasing exponentially with time constant. Doing the exact same thing, at the second section, the circuit is equivalent to exponentially increasing current source driving parallel RC network, where R being the characteristic impedance, and C is the capacitance of the second section. There is a finite duration at which the entering current is increasing exponentially, before settling to the constant value. So the current entering the second unit capacitor initially increases exponentially, charging the capacitor till a point after which the current entering the resistor starts becoming significant enough to reduce the current into the capacitor back to zero. At the same time, the voltage at the capacitor increases exponentially and finally settles to 0.2 volts when the current goes to zero. Notice that the 0.2 volts is the voltage of the transmission line as a result of the voltage division in the input. That process repeats itself over and over and over again at each section. Each capacitor settles to 0.2 volts after some amount of delay based on its location on the line. Here we see the voltages and currents across the first 5 caps, cap number 25, 50, and 75. Each cap represents a point in the line, and each point has its own delay. As you can see, the delay becomes more and more significant as we move along the line. The 0.2 volt signal at the input propagates through the line and reaches the end after finite duration known as transit time. Propagation acts in form of charging the capacitors gradually one by one to 0.2 volts. The voltage at the input of the line is 200 millivolts from voltage division, let's call it V1, and injecting constant current during that trip, irrespective of the current of termination. When the signal finally reaches the end of the transmission line, the voltage at the endpoint becomes V2 depending on the value of the termination resistance, so that the ratio of the voltage over the current equal to the load resistance, and the current drawn by the load resistance settles at V2 over RL. Starting from the nearest LC segment to the output load, the current in the inductors and the voltage across the capacitors start settling to I2 and V2, tweaking themselves to that of the load. And this keeps on happening back to all the sections till reaching the input. This is known as reflection. To see the effect of reflection, let's tie the input and the output nodes to the oscilloscope, where the line is terminated with different kinds of loads. When the line is terminated with 50 ohm resistance, the same as the characteristic impedance, the input of the line settles to 0.2 volts. That 0.2 volt signal will propagate through the line, charging each capacitor one by one to 0.2 volts till reaching the load. The voltage at the load end is zero until the signal reaches the load after about 510 picoseconds of propagating, and then settles to 0.2 volts. Since the load is equal to the characteristic impedance, the whole signal will be dissipated in it, and there is no reflection. This is known as the matched condition. The load is equal to the characteristic impedance of the line. Now let's terminate the line with 80 ohms load. As you know, the voltage source at first will see the characteristic impedance, and the voltage settles at the input to 0.2 volts based on the voltage division. Time passes and the voltage at the input of the line is fixed to 0.2 volts. At the same time, the 0.2 volt signal propagates through the line, settling each capacitor to 0.2 volts, then reaching the load after 500 picoseconds. Once reaching the last section, the load will say, "Sorry Mr. Signal, I'm not 50 ohms anymore, but I'm 80 ohms." Now, same current driving higher resistance gives us higher voltage, 245 millivolts. But all the capacitors as well as the load are connected to the same point. So starting from the last section, each capacitor starts to settle to 250 millivolts back to the very first section. Now each capacitor starts with 0 volts. When applying the input signal, the capacitors gradually charged one by one to 200 millivolts. We call it a 200 millivolt signal is propagating through the line. When it reached the load, by the effective reflection, each capacitor gradually moves up from 200 to 245 millivolts. So it feels like a 45 millivolt signal is moving backward toward the source. After about 1 nanosecond, the reflected signal reaches the source end. The 200 ohm source resistance will force the voltage at the input to settle at 270 millivolts, generating a voltage difference of 25 millivolts. That voltage difference will propagate back to the load, charging each cap to 270 millivolts. These reflections take place back and forth until the input and the output, as well as each point in the line, settles to the same voltage level. At that point, the source is seeing the full 80 ohms load, and the final settling voltage is defined by the voltage division between the source and the load resistances. The larger the difference between the load and the characteristic impedance, the more will be the reflections. The ratio of the reflected to the incident signal is called the reflection coefficient. It depends on the difference between the load and the characteristic impedance. Now at first, the voltage at the input settles to 200 millivolts. That's because the voltage source sees only the 50 ohm characteristic impedance. Finally, after all of these back and forth reflections, the 80 ohms load isn't hidden anymore, and the circuit settles to 286 millivolts. Voltage division between 80 and 200 ohms. Let's terminate the line in this case with load less than the characteristic impedance, say 20 ohms. At first, the source sees only the characteristic impedance, so the voltage at the input will settle at 200 millivolts. That 200 millivolt signal will propagate toward the load, settling the capacitors one by one to 200 millivolts. After about 500 picoseconds, the signal reaches the load. Since the load is less than the characteristic impedance, the voltage on it will settle to a value lower than the 200 millivolts, depending on the difference between the load and the characteristic impedance. In this case, 113 millivolts. All the capacitors will settle backward to 113 millivolts till reaching the source at around 1 nanosecond. At that point in time, the voltage at the input will settle down to a lower value due to the resistance difference. That series of reflections will continue back and forth until the whole points in the transmission line settles to the final value, around 91 millivolts. Once again, 91 millivolts is the result of voltage division between 20 and 200 ohms, since the load is finally visible to the source. If we set the load as open circuit, the voltage at the output, as well as that in the input, will finally settle to 1 volt after a series of reflections. At first, the voltage at the input settles to 200 millivolts, then settling the output to 400 millivolts. Then finally the input and the output, as well as each point in the line, will finally settle to 1 volt after a series of reflections between the input and the output. Similarly, when shorting the output, at first the voltage at the input settles to 200 millivolts, then finally settling to 0 after a series of reflections. Notice that the voltage at the output is always 0.